Yeah.
What's the lab?
So lab today is a computational one, and I need to review that one myself because I was realizing as I was looking at the lab that I haven't done this lab or any computational stuff since 2022. So it's been a few years. Everything seems like it still works the way it's supposed to work.
I haven't talked to Ice Table since I had your class. I was able to help them out.
It's true. It'll come back, but I gotta sit down and make sure it comes back.
Yeah, I have a that. So
We'll make sure it won't go the whole time. I'll get you started. There's enough good tutorials, and I did a good enough job documenting the process. That we should be good to go with that. And then we'll get output files that look like this, where actually minimize it. So this looks like just a regular ethanol that we would have built, but this is the output file rather than the input file. And it actually is a geometry optimization. So this is the input file, has these specific coordinates. And if you look at the bottom, it's got 4 different frames, each with a different energy.
Oh.
So it actually, when you get the output file, it gives you the potential energy surface of the process. So you can actually look at the energy of the optimization, but in the most stable geometry is the one that it's going to end at, or at least the one that's closest. There might be another potential energy minimum, but we'll go over that in more detail. Just since I just ran that one and I still had this opened up. And I guess just to give you, as long as we're here, open that for back, but the actual, yes, but if you just open it up as with a text editor, which I don't have Notepad++ installed here on this one. You basically just get your output file is just this giant list of coordinates, orbital energies, stuff like that. So obviously this isn't very easy to parse on its own. It's got a ton of information in there, but that's what MacMold PLT is designed to do, is to take this output, pull all the relevant information from it, and put it into a form that we can then use.
Yeah.
Right. So and if you actually wind up doing this on a long term, if we were actually doing this for research, you basically wind up finding like certain keywords you always look for. Optimization complete will always get you to the numbers at a specific point that have certain information. And it's
I guess downward, there were a couple of different, it's a minimum value.
I just can't quite read it from this angle. So this is on the screen here. Where
Yeah, it's values instead of like -1x and
this.
Yeah.
So these are the control options are basically the calculation method that we're telling you to use. So DFT type is a type of calculation. We're not using DFT for this first one. We're using Hartree Fock, which you mentioned at one point. You saw that name come up.
Yeah.
Hartree Fock was the basis, was the first computational chemistry, and then DFT's density function theory came along and scales a little bit better. DFT scales into the 3rd instead of into the 4th. It gets slightly better numbers. So when you want better numbers, you can use DFT type. If you want it to be more strictly ab initio, you use Hartree Fock. And then all these other things put in here. Multiplicity is 1, means there's no unpaired electrons. the other options, but we'll talk about all those in class. In the lab today, but basic. It is, well, and you can see how even, these are the numerical methods because you can't solve it analytically. And, even that still winds up being pretty nasty. It's doable. That's why we have supercomputers. All right, so let me pull up the chapter talking about aldehydes and ketone, or that was for the aromatic substitution reactions, huh? There's our reaction summary. There we go. Where's the
So there was a mechanism for it,
and it's okay, so
and
it's
then there was also just a regular reaction question for it, what it was. So,
yeah. Let me I was in the wrong chapter looking for it. So that is you're right. We didn't get to the Baeyer-Villiger oxidation.
Baeyer-Villiger, I was like trying to remember the name, but I was like,
Yeah.
something with B.
I must have just left it off of the slides for some reason. I must have shortened them. So Baeyer-Villiger oxidation basically inserts an oxygen in between a ketone in one of the R groups.
So it just turns it into an ester.
Yeah. And the mechanism is here.
So is this gonna be on the exam?
It will be on the exam. Let's talk about it real quick. The mechanism isn't as long as it seems. It's got a weird intermediates. We do make a peroxy bond. We start with a peroxy acid, and that oxygen, the peroxy oxygen, is a pretty strong nucleophile because it's that oxygen single bond is pretty weak. And so basically you get a nucleophile attacks the carbonyl carbon, and you make a tetrahedral intermediate where we have two oxygens attached. And because it's a peroxy acid, we've actually seen this proton transfer, this intramolecular proton transfer. This is actually really similar to what we saw to the epoxidation reaction, right? The epoxidation reaction was the same peroxyacetic acid attacking an alkene. And we had something similar happen at first. And we have this 5-sided ring that allows us to make a proton transfer. So carbonyl oxygen on the peroxyacetic acid winds up grabbing the hydrogen. And the peroxide oxygen holds on to the electrons. So basically nucleophile attacks carbonyl carbon. Rearrangement just shuffles the proton over to the other oxygen. And we get this intermediate, which then just goes through a rearrangement where we shift one of the R groups over to the oxygen, to the peroxide oxygen, and break the peroxide bonds. And so the net result is we just insert an oxygen in between. And I believe we get a mixture of the products. Our two R groups are not symmetrical. We're gonna get a mixture. Although I think it's gonna favor the smaller R group doing the rearrangement. Which would make sense, right? With rearrangements, the smaller object winds up rearranging faster, methyls transfer faster than ethyls. I think you'll still get some of both products, but in general, when you do this rearrangement, if these two are not the same R groups, the smaller R group is gonna actually do the rearrangement more often than not. Yeah. Yeah. No, actually, I had that backwards. The migratory aptitude. So it's gonna follow stability as a carbocation, because we actually have to break that sigma bond to do it. It's not. The reason it's not following our same rules as before, where a methyl goes faster, is because those rearrangements, we were moving towards, it was a carbocation rearrangement, we were moving into an empty orbital. Here, because we're moving into a lone pair instead, it actually follows carbocation stability rules. So tertiary carbon will migrate faster than a secondary, and phenyl are relatively the same. And then primary or then. So if it's an aldehyde, we just make it carboxylic acid. Because the hydrogen moves faster than anything. A hydrogen ion is more stable than any carbocation. Right, so if we had to choose between the phenyl group versus the hydrogen is going to be the one that rearranges so that we get a carboxylic acid. But if they're both if they're both alkyl groups, then the more substituted carbon migrates faster and hence is the bigger product, the major product.
So the sigma bond was breaking is between two isotopes, two.
Yeah, let me go back to the. So we have to, because we're not dragging a methyl group over into an empty p orbital. That's the difference in our rearrangement. Now we've covered all of them.
It's Bayer, is that like Baeyer-Villiger the whole?
I believe not. Because there were actually a bunch of German organic chemists named Bayer. That some of them are related and some of them, but I think most of them are not, because this is a Bayer with the E, not Bayer, just Bayer. It's not just an anglicized version. I think it's a different person.
Is it like?
Correct. Adolf von Baeyer and Victor Villiger in 1899. So I believe they would have been contemporaries. because that's roughly the same time period as aspirin was first made. That let's see, Adolf von Baeyer. The link to the Wikipedia is purple, like I've clicked on it before. He was a student of August Kekuli, of the Kekuli structure. Then let's look at aspirin real quick. First discovered. Drug from Bayer. Friedrich Bayer, without the E. So not related to Adolf von Baer. Yeah. I mean, it's all very stereotypical German names, right? Friedrich and Adolf. All right. So a couple steps. The trickiest one here is that rearrangement in the middle and then a carbocation or a moving a carbon over rearrangement as your acid leaves. Right. All right. Did you have any other things pop out at you, Jerry, on the practice test?
Oh, yes, number 3 of the reactions.
Number 3 on the reactions. Let's look at it.
This is more hydrated. Yeah, but the part after.
So the fact that you're losing a hydrogen or losing water, it's a dehydration reaction.
Yeah.
So you're going to start by, when we do one equivalent, one of these is going to wind up reacting, being reduced to make it an alcohol, right? So our intermediate, not our intermediate, our first answer. Yeah. Just pick one, doesn't matter which one. Yep. And remember, alcohols in an acidic environment, especially if heat, especially if I'm telling you it's a dehydration reaction, we're just going to turn it into an alkene. Right, so there were a number of ways you could go through a dehydration reaction, but I'm specifically just telling you, hey, it's a dehydration reaction. What is a dehydration reaction of an alcohol going to give us? It's going to give us an alkene here. I don't really see. I'll do our ketones. Do ketones undergo dehydration reactions? They do, but not typically just with acid, right? Because if you try to follow a mechanism through there, if we protonate, let's say we try to do a dehydration on the other one. We protonate there, we've got a positive charge there. We don't really have like a good nucleophile that could come in here and attack in order to do a dehydration of the aldehydes and ketones, we needed a good nucleophile, right? And then we would get the enamines and the imines and all those. We don't have a good nucleophile here. So really just looking at the oxygen as leaving through.
I think I have one more.
Okay,
That was number 10. These reactions.
fuming. So. First step. Nitro group with a good leaving group in the para position. So that's going to be our nucleophilic aromatic substitution,
Oh, I always forget that you can do it with.
right? So we have strong nucleophile, strong withdrawing group in the para position, and a good leaving group. So first step
Would be the
we're going to get so a strong electron withdrawing group and a strong donating group, activating group. So then our next one, fuming H2SO4, is we're going to add an SO3. And we've got an OP director that's strongly activating, so that one takes priority.
So.
Can't go para, so it's got to go ortho.
I think it was just that first step that was confusing me. I forgot that you could use other things than like.
Yeah, no worries. This is why we're doing the review, right?
I saw the O2N, I was like, I didn't see that before, but I was like, NO2 can only be SNAR.
And if it said excess fuming H2SO4, we'd wind up putting the other one right there. Is there a what? There's not on the practice test. The test, if you count up the points, there's 5 points left. There'll be a 5-point wild card. That's gonna have something to do with electron donating versus electron withdrawing and resonance structures and electron density. So it'll be a conceptual, a little bit of a surprise, but it'll be tied to some of the concepts we spent a lot of time on. Comes mechanisms. So with these, electrophile generation, right, is the tricky part, and then all the electrophilic substitution. So I'll go ahead and just tell you one of the mechanisms is going to be electrophilic aromatic substitution. So I can switch up what the electrophile is. I can switch up, what the substituents are to make it so that you have to think about meta versus OP. So there's some variables there, but it's going to be one of those. Aluminum chloride or fuming sulfuric acid or the nitronium ion, maybe even Friedel-Crafts. Then there's your Baeyer-Villiger. So I know we just learned this one, but what would the product wind up being? We have to insert an oxygen between the carbonyl and another carbon, tertiary or phenyl. Where are we going to put the oxygen? on the tertiary side. So hydrogen is the ideal one, hydrogen moves the best. And then you go tertiary,
Secondary, primary.
secondary and
secondary.
methyl are roughly the same, and then primary, then methyl. Right, it follows our rules for carbocations.
Oh, it's gonna be products.
Yeah. We'll just say the major product for these mechanisms, you don't have to show the mechanism for the minor products. That'd be a lot of writing.
Will you be showing what product will be going towards, or is it just gonna be blank like that?
I didn't when I wrote the test last time. I'm open to being convinced otherwise.
Yeah, I missed that. So,
The question, am I gonna give you what the product is on the mechanism side? I didn't when I wrote the test last time. But if I'm asking you twice as many reaction questions, then I suppose I can give you the product on the mechanisms. And the nice thing about these OChem tests is, yeah, there's a lot of material and a lot of stuff on them, but taking the test actually doesn't take that long. It's nobody's running out of time on these.
it's like you never,
Yeah, the mechanisms are getting to the point where you can kind of fudge your way through on some of them, but it's not comfortable and not advised.
You allow a little bit of part of that. Just, we have so many mechanisms at this point.
Okay, well, we have 2 out of the 3 of you here, so here's how we'll do this.
I don't like voting in this kind of style where there's someone not here and we're all uneducated. how it's
What?
happening.
No, so treat it more less of a vote and more of a discussion.
But you take.
You can either get the mechanism products drawn for you, or you can have a 3x5 or a half page note card, half page one side.
Okay, so do you know the implications with getting? Because I know he's gonna make it harder.
Yeah, absolutely.
I know he's gonna make it.
I don't always.
Well, I mean.
We have covered a lot of material in this class, and I'm saying with having as many reactions as we do, kind of everything's fair game. So now is the time when it would be appropriate to do a note card. And then not have the mechanism or the products given on the mechanisms.
Well, that'd be fine if the products are not on the mechanism.
And then no rabbits out of the hat from there.
And no rabbits out of the hat.
That's what you screwed up.
I'm not gonna dramatically change the test.
All of that, yeah.
Well,
Okay.
because
So
I'm just
Because
using
if I
my
don't-
professors doing.
If I don't know the mechanism, then I'm not gonna be able to use the product. Anyway.
That's true.
right. So we'll say half of an 8.5 by 11 sheet, one side. Is that enough?
That should be.
Just one sheet.
Let's do one full sheet, not half sheet. You get one letter size printer paper or binder, like lined if you wanted or whatever. One side of one piece of paper.
This is 10 by 7. So.
So you're shooting yourself in the foot there a little bit, but we've got 8.5 and 11 if you need some 8.5. Yeah, one side of one piece of paper, note card. I'll go find him after we're done here, and I'll tell him we decided that in case he doesn't see that on the recording.
That's what we've been doing in business, with so many equations that we're gonna have to. It's better than memorizing.
In Gen Chem, the way I justify is I give you the equation sheet. You have to know how to use them though.
Exactly.
But here there's so much material in OChem at this point. That I'm fine making doing a note card for it.
And then, of course, I'll give you your safety blanket, your periodic table that I don't think anybody's gonna need at this point, but.
It's the untouched paper.
Yeah.
Right here out. It's nice and clean.
You don't need it, but you don't wanna need it and not have it, right? All right, and then was there another Baeyer-Villiger on
Yes, they're, wait.
right there? We did the mechanism one.
Yeah,
We didn't look at this, so here we've got a methyl versus a phenyl group. So our phenyl group's gonna be the one that rearranges. So our product. And then. We're gonna brominate. The. Yeah, sorry, the benzene.
and it will still be orthopara just because the first constituent that's on it is.
It'll still be orthopara because, yes, because the lone
Because the
pair is
resonate.
conjugated.
Yeah,
There is a pi bond, but the pi bond's not conjugated.
right, yeah.
So we'd want, it would be OP, and with this size of a constituent, probably para is your,
So that's kind of the chunky.
yeah.
Would it be both?
I would mark you down either way, if you said just para is the major product, or if you said you wrote the ortho and para products.
But if we wrote the para, we say like major product.
Yeah.
Okay.
If I said ortho was the major, I'd probably get rushed down.
I mean, even that,
What was
An
the
argument could be
statistics
made,
game?
that's the statistics game, there's two carbons that are ortho. But they're sterically hindered, that's that balancing act.
Right.
I'm not gonna get picky either way on those.
But technically ortho is favored in the reaction. Normally,
Depending on how big your group
so
gets.
yeah, statistics game, so you
So
can choose.
because it's a balancing act and it's gonna be in that gray area where you've got competing variables. I mean, I wouldn't feel comfortable
Right.
saying it's. So the way that I would answer this question is I would draw both the ortho and the para. And I would say, and then if push came to shove, if I had to pick a major product, I would say the para is the major product and I would specify because of sterics. So that I could put my logic down.
Yeah.
Not every professor gives partial credit for explaining your logic like that, but. You can feel better about it, and then when you come back and argue for points with them later, when they don't give partial credit, if you have your logic on there already, then they are more likely to, like, well, I guess you're right. Which. I'm not sure how many of you, like, I don't want to encourage going and grade grubbing for extra points on tests necessarily. But if you ever do need to go make your case. Self-advocate for a professor, especially once you leave LTCC. Have your logic well defined ahead of time. I almost had to repeat a class in grad school because I didn't have the prereqs when I took the class. Because I may have fudged my resume a little bit and they verbally on the interview to get in. Like, oh, differential equation, we're a semester school, so our differential equations class is kind of folded into top 3. Which is kind of true, we did like 2 weeks of PQ. And so then I got into the
grad level diff EQ that presumes that you had undergrad level diff EQ class. And it took me the entire class to figure out what was happening. And so I almost didn't pass, but I had the highest grade in the class on the final exam. And like first midterm, I was the lowest grade in the class, and then I was squarely in the average on the second one, and then I had the highest grade on the final. And so I made the argument. I had like, look, see my progression. Clearly I get this stuff. Was able to talk my way out of repeating that class. So if you do need to make that an argument like that, make it logical. And don't make it about, well, I need these points. Make it about, well, but here's what I was trying to convey. All right, that's just life skills though. Academic life skills. All right, anything else on here?
I mean, it was a lot of review. I had to pull out the OChem2 text or like.
Yeah.
But
I pulled out my little two for this.
I mean, but once I started actually looking at everything, it kind of clicked back and
Good. All right,
it should be fine. I think for all the rest of them, yeah. They're pretty straightforward.
well then, we can, if we want to take a 10-minute break and then come back, when we come back, we can either, or we can use the rest of the class period today to start working on making your sheet of notes. Or we can do the intro for the lab. And you can use your lab time this afternoon to go study in the library instead of coming back at 1.
But, so,
Yeah.
Okay,
I feel like it could be better.
let's take a 10-minute break and come back at 1:45 and we'll talk about computational stuff for a little bit.
Using that program first was like. It was like really frustrating, but like yesterday it just clicked.
Good,
Like doing all the. Like the different Z matrices, it clicked. And I was
Good.
like, oh, wow, okay, I didn't realize that.
it's just another way, it's another coordinate system, right?
Yeah.
That
Just have to get used to it.
right. There are some things where spherical coordinates work better than Cartesian, and there's some things where Z matrix works better than Cartesian.
Did we have to do the ethanol? Looks like I did it.
We're gonna use ethanol in today's lab, so if we did it, then I'm gonna set you up to, okay, and be in better shape. It's going fast, huh?
I got 64 on my physics.
Ooh, got some work to make up there, but you got time. Better than zero. I don't know what.
Stuff that I'm more familiar with, like pressure and stuff like that, so,
Yeah. That'll help.
yeah, familiar.
That's fair. All right, so. I'll give you a second to pull this up. So we're kind of combining two two assignments here. The one that's labeled lab 3 is the actual what I actually want you to submit here. This is going to be what your actual assignment, I guess. Well,
What does it say lab 3 on the actual?
sorry,
Oh, so the intro to games.
intro to games has the actual thing, but it's kind of bare bones. It's basically here, build your geometries, optimize geometries, find the transition state. And it's going to be for a concerted hydration, which is not a mechanism we've studied because it's not a very stable mechanism. But basically, if you took water and you just brought it straight up to an alkene. So let's say we have ethene, water. So one of the reasons why computational chemistry is kind of tricky is that it's all presumed to be happening in gas phase, which means it doesn't really favor making intermediates, especially charged intermediates, because in the gas phase, those are exceptionally unstable because they don't have any hydration or any solvents to stabilize them.
Form, if they
Right.
do, it's like so short that.
Exactly, but the problem is, so we know that, but the problem is that we don't really have a good way of simulating solvation energy in all these pods. So if we wanted to try and say this is happening in water, we would have to basically surround this molecule with water molecules that are then can orient themselves and point their partial positives towards partial negatives. But then we start increasing our number of atoms and number of electrons really fast when we try and do that.
Takes a lot of computational power.
Exactly, because remember these things, especially Hartree-Fock, we're gonna be using to start these. Hartree-Fock scales as n to the fourth. So double your number of electrons, that's 16 times longer to finish the calculation. So we're going to use a mechanism that's not the real mechanism for how hydration happens. We're going to be looking at it like it's a concerted mechanism, because in the gas phase, if it was going to go through hydration, that's how it would actually happen, because then we don't make any charged intermediates. Normally, we would say, okay, you protonate one of these, make a carbocation intermediate, which is then a good target for a nucleophile to come in and do the two-step process, right? But what we're gonna do here is we're gonna actually calculate what the energy looks like for the concerted state, where we're just actually gonna be looking at the transition state, or where this pi bond is breaking, and we're making bonds and breaking bonds simultaneously. Right, so we're not expecting this to give us a activation energy that's actually gonna, match what we see in experiment, because we're making some of these assumptions. It'll be similar to what we would see if we actually did this reaction in the gas phase, but not in the way we actually see it in lab. Right, so the process, what we're trying to do is we're going to find the energy of ethene and water separately. We're going to find the energy of ethanol, which is our product. And then we're going to find the energy for this transition state to make a really crude potential energy surface. Right, so those are called single point energies. We're going to optimize the geometries using Hartree-Fock, because that one scales, it doesn't scale the best, but it's relatively quick, and it's known for giving pretty good geometries. It fails at giving the energies for the geometries, but it gets the geometries close to being right. So then we're going to take those geometries from the Hartree-Fock, and for both of these, and we're just going to use this other function, this other calculation, which is a type of DFT. It's a type of density functional theory that we mentioned earlier, that we were talking about earlier. Hey, how's it going?
Dylan's got hit in the head and now hurts badly.
Okay. Well, if she can hang out with you until noon, I think we're gonna be done at noon, and I can take her home.
You can see her at school in the environment.
Okay. Yeah, it's fine. I can go pick her up when we're done here. She can hang out, that's fine.
That always works out somehow.
Well, it's I don't want to say that what happened to her is not serious, I don't want to minimize it, but her older brother is home sick yesterday and today. And she was the only one who went to school yesterday, and so I think maybe part of this is worse because she's at school and her brother isn't. She also wants to have a sick day. So, anyway. For what this will do is this is known for giving better energies. The energies more closely match with experiment. If we use this, so we'll use this Hartree-Fock method to find the geometries. And then we'll use this MO62X to get the actual energies. And so just as the other more detailed lab procedure, the one that's labeled lab 4, I actually have a demonstration of why we use both of these methods. Look at that, MO62X almost circled when I switched tabs. That's funny.
That's you.
If you actually look at taking 1,3-butadiene and rotating it from the S-cis to the S-trans, the S-cis that's perfectly planar, one thing that's kind of interesting is the S-cis, when it's perfectly planar, actually is not a potential energy minimum, it's a potential energy maximum. Because you actually have these sterics where they're kind of like butting up against each other. So it actually is more stable, kind of like the twist boat. When we go thinking back to cyclohexane, the twist boat was kinked just a little bit so that you could avoid some of those sterics.
So like a triphenyl.
Or like,
methyl,
yeah, that's right. They're never going to be perfectly planar so that they can avoid the sterics. So if you actually just look at these geometries though, and these energies, the RHF, the Hartree-Fock versus MO62X are slightly different. And the MO62X more closely match the energies that are measured in lab. We actually look at equilibrium constants, we can figure out what these energies are relative to each other. And you'll notice that they're almost identical energies when you look at the. Actually, I don't think we can say that. Never mind. I had to pick a 0. So I picked both of these. This point is set to 0. So by definition, they're going to be close there because I set them.
And the farther away you get from that,
But yeah, so but you'll notice that so the MO62X predicts that they're more stable over here, but then higher transition state energy, it more closely matches with what we see in reality. So basically, a lot of times when you're doing computational stuff, you kind of mix and match methods based on what their strengths are. If we're doing anything that involved, like even just something as simple as the Diels-Alder reaction, anytime you've got multiple orbitals forming and breaking at the same time, then neither of these methods work. You have to start using what are called excited state methods, where you're taking into account the fact that you could be putting electrons into the LUMO. These are both assuming that no electrons are going into a LUMO anymore. So as soon as you have anything involving excited states, you have to use more complicated methods that scale even worse. So it's one of those things that the more time you spend in this field, the more niche it kind of gets, because like, okay, well, I study organic photovoltaic materials, so I need to worry about excited states and band gaps and HOMO-LUMO gaps, so I have to use these more complicated methods. Versus a lot of, after finishing this assignment, YouTube will actually know more than some grad students that publish work using these calculations, because a lot of, and I'm gonna shit on experimentalists a little bit. Because experimentalists will measure the rate of a reaction and they'll say, well, I think this is the mechanism, and they'll just throw some calculations in so that they can support the mechanism that they think it is already. But they don't actually understand where the methods work or don't.
Yeah.
And so there's, that's part of the rivalry, I guess, if you want to call it that, between computationalists and experimentalists, is that if you actually know where the methods fail, you can do a lot better job at actually matching reality with your calculations. But you're putting yourself into a box because now you have to say, well, I've never actually run that reaction before, but I predict that it'll be like this. And then you have to find an experimentalist who will actually run it. So there's always a back and forth. In computational groups almost always work very closely with experimental groups. And it kind of is a back and forth. Experimentalists will say, well, we don't understand why we're getting this result. Can you explain it? The computational will say, well, we can explain your result and we can actually predict this one might work really well. Would you try that? And so there's a back and forth. It is actually a pretty healthy working relationship. It's a friendly rivalry, for the most part. All right, so this file, the one that has this labeled as lab 4, has more information about actually running the calculations. And so we're going to run through how we do this, but basically these other 2 files here, these sample files, they're labeled as .inp, but basically you're going to want to open them with a text editor. So because it's a bit of a holdover from the way that you have to submit the jobs when you're running them on your own computer. You have to have an input file in order to submit it to games to actually run the calculation. But they basically work just like a text file. So
like the
Notepad ++ or brackets or so, and since I don't have Notepad ++ here, I'm just going to open it on. In Notepad, but it'll look pretty similar. But basically, all of this is basically telling the program what settings to use to do the calculation.
Oh, I see, yeah.
So initially you want to say, okay, well, it says SCF type equals RHF. R stands for restricted. The HF is Hartree-Fock. The restricted means basically we're not allowing our orbitals to be partially filled. Orbitals either have 2 electrons in them or 0 electrons in them. So that's where we're locking it into ground state. This is the sample opt RHF. I charge, and so that anytime when you see these games, this is called commenting or commenting something out. Basically, when you hit a exclamation point, that's basically telling games to ignore the rest of the line that comes after that, so that we can leave ourselves notes.
Oh, so like, yeah, I see, like charge of system, calculation type.
Right, if we got rid of that exclamation point when we tried to run this, games would say, charge of system, I don't know what that is, fail.
Yeah.
It'll just crash out, because it's gonna try to tell it to do something it doesn't know what to do. So we tell it its comments. Run type is the type of calculation you're doing. So if we wanted to just do a single point energy, if we already have the geometry that we want, we would just write energy. If we wanted to optimize means it's going to try several geometries and find the most stable of them. So kind of approaching the bottom of that potential energy well.
It says see manual, is there?
There is a manual, so you want that.
I don't think I have that linked, but the games manual is online and it has a list. But it's 200 pages long. But if you open it up, Control F for run type, and it'll have these are your options for run type. The 3 that we're going to care most about for right now are energy, optimize, and SAD. And SAD point is we're looking for a saddle point, meaning we want the local maximum in 1 dimension. Okay. So we always think about these potential energy surfaces in 2 dimensions, but basically like this, right? But they actually are an n-dimensional system where n is the number of
nuclei. So a set, when we're looking for a set point, we want it to be a potential energy maximum in one dimension and a minimum in all others. So basically, if we just think about it as a three-dimensional shape. This looks like a bowl, right? And then here, it's still concave up in the in and out, but it's concave down in the other two. And it actually runs the calculations and it says, okay, I'm gonna try to minimize in this dimension, find the local minimum in all the other dimensions, but local maximum in one dimension. Exactly. Yeah, I mean, that's exactly it. Yeah, except it's n-dimensional, not just three-dimensional.
Yeah.
So that's, if we're looking for a transition state, we always want static. If we're looking for optimized geometries, products and reactants, we just want to write optimize. Because for our products and reactants, we want it to be concave up in all dimensions. For these first ones, DFT type equals none. And if you write none, then it's gonna just calculate your Hartree Fock. We just trade that in for, there's basically, they call these anything that starts with the M, it's called the Minnesota functional. Because it was developed by University of Minnesota, and there's probably about a dozen now. MO6, when I was working in grad school, MO6 was the best for organic systems. Since then, I think there are other new ones, but we're not gonna mess with it right now. Basically, you use different DFT functionals for different systems, and they're constantly being tweaked and improved. So we'll use this one, but it's pretty trivial to switch that out for a different density functional query if you want. For a different DFT functional. This you're not gonna need to mess with, but basically it's really easy to write a calculation that takes way more computational resources than your system has. And if you do that, it'll hang up and it'll just never end. And you're not sure why, and then you have to kill the job and look at the log file, figure it out. So if you're not sure if you're gonna be able to run the job based on your system, you run it as a check. And it'll basically test how much memory you have. It won't check your processing power, because basically if you give any processor enough time, it will eventually finish. But you can actually wind up, if you run out of memory, it just full stops and soft locks the system.
So it won't have enough space to actually hold the calculation temporarily.
Exactly. So, but whereas having any modern processor will eventually finish, it just might be like several years from now if you're not careful. But it will still be making progress that whole time.
Leave that tab open, you don't know why your computer's running so slow.
Exactly. Well, luckily, we're not actually gonna run these locally, so it won't be on your computers. We're gonna submit.
Oh, did you
these
figure
to
it out?
the online system? Yeah,
Are they still doing it?
They are. I ran a job this morning. So when it's on here, so. Oops, I didn't mean to do that. Web games. Takes you to.
And you just submit a file with that.
And yeah, so we'll work through that once we're done talking about these input structures. But basically, you're just gonna go straight to submitting a job. And then it has a system built in to build your own input files.
So you can just build it on.
Or if you build your own, you just come down here to the bottom, we're gonna copy and paste in here and then just hit submit job. But again, I'll show you that and it's like, for example, one of the reasons why I don't use this to do it is it doesn't have the MO62X functional that we actually want to use. It has just the regular MO6 functional, which isn't going to give us the right answers. So we're just going to do it. We're going to make our own. I guess you could play around with this if you do generate. Yeah, if you make your your geometry winds up being up here. There you can go submit your own files. And then you can just browse the file, or if you go to the guided submit, you can copy and paste and just put it right in here and everything will run. Before we get to that though, the rest of this stuff, basically, and a lot of this is holdovers. This is actually kind of interesting historical footnote. Before, so everybody knows what a byte is, right?
Yes.
It's versus a bit. So a bit in computer science is one piece of information, either a 0 or a 1. But that's not enough to actually convey an entire character. Like a single letter actually requires
a bit.
no. A whole character actually requires 8 bits.
Oh, okay.
Because, and you can think of it basically like, if you think of an old school digital clock. Oh, yeah, 1, 2, 3, 4, 5, 6, 7, and then sometimes there's like a slash in there. So basically you need to tell each one of those spots on or off. So that actually takes 8 pieces of information to carry 1 character. To say, is it an A or is it 9 or is it B, whatever.
Oh, God.
So a byte is 8 bits. And so then because computer scientists were being clever, they said, well, we're gonna say that 8 bytes is a word. Because, you know, you put 8 letters together, you get a word. So basically they're working on a base 8 system. And so they actually, in games was written long enough ago, the original programming was written long enough ago, they were still using that term. So a mega word is 8 megabytes.
A mega word.
And you actually have to specify it in mega words.
They should WOURD.
Words. So anyway, you're not gonna have to mess with any of this. They eventually added in, actually, all the way back then, you could run the same calculation over multiple processors. So they were actually doing processing in parallel a long time before computers had multi-thread processors. You would actually just have to run it across multiple computers at the same time. And then actually what ends up happening is the communication between the computers is actually your bottleneck. Pretty quickly, you actually have to have a fast enough connection between the computers so that they could send the information back and forth if you're gonna do it in parallel. So anyway, you're not gonna need to change any of that. Or this. This is basically. You always have to start from an initial guess for what your orbitals look like. And sometimes your initial guess can be far enough off, or it can be wonky enough that you actually get hung up where in an oscillation where it just goes back and forth, it never reaches an actual answer. It gets, this answer is wrong, so let me try this answer. This answer is wrong, but then it bounces back to the first one. And it never makes it to the bottom of the potential energy well. So sometimes you have to change what your initial wave function looks like. But again, you're not gonna have to mess with that.
What would be the mode?
So Mo read, if you already have a better guess from a different system, where your nuclei are all in the same spot, but you used a different, like maybe we wanted to use that RHF gave us a real answer, but all these different DFT functionals won't. We can basically say, okay, take the RHF orbitals and start with those as your initial guess. So it allows you to take the wave function from another method, from another computational type, and read it in as your starting point. As opposed to, this is actually the Huckel guesses is basically, remember the Huckel rule was we were talking about aromaticity and the energies. Basically you can get a really rough guess,
by just looking at where the atoms are. And so that's usually good enough. The other reason that you might want to read in an orbital is you start from really bad, yes, even if it'll eventually get there, some of these computations, every time it calculates the energy of a new guess, might take an hour. And so if you have to do it, if it takes you 75 iterations to get to the real wave function, and every one of those took an hour to calculate, now you're running a 3-day-long calculation. So some of those times it can be really helpful to start from a really crappy method, really cheap computational method to get your initial guess, so that it only takes 2 or 3 cycles with the more expensive method. It's been a long time since I've done any of this, but it's mostly coming back. This is one of the ones that actually winds up being important. This is called the basis set. The basis set is basically what orbital functions are we going to mix together to make our molecular orbitals. So basically it's just a series of atomic orbital functions. And basically the more of those different orbitals that you have to mix together, the better your answer will be usually. But there is diminishing returns, because as you increase the size of your basis set, so basis set comes from the term, this is the basis that all of your molecular orbitals are made from. It's basically what ingredients do you have to mix together to get to your molecular orbitals, which are going to be some hybrid of all of them, right? So the larger your basis set, the better your answer will be, but the longer your calculation will take. So this whole system is set up so that in a way that allows us to very specifically expand the basis set as needed. So the G basis is the number of Gaussian functions that make up your valence orbitals. 6 has to do with how many orbitals we're allowing it to show for the core electrons. For the most part, core electrons don't really change anything, because those core orbitals that are filled all the time don't play as big of a role, but it turns out they do affect the overall energy of the valence electrons. So the more core contractions you have, the better your valence energies get, the better your overall energies get. Number of D functions. Actually, it's not currently set to 6-3. It's set to 6-311 plus G double star. Number of D, basically this allows you to put D orbitals on anything that's not a hydrogen to mix it in, because those other orbitals, those D orbitals are there even if they're not filled, right? So it allows you to mix in some D orbital character. And same for putting P orbitals on hydrogens. It allows every hydrogen to have one P orbital that could get mixed in with its S orbitals, for the sake of getting, because there might be some small amount of P orbital character mixed in that actually lowers the overall energy of the system. And then diffuse functions are what we represent with these. The stars, basically like a larger version. So like there's the 2s, and then there's like this star basically says, well, what if the 2s was a little bit bigger than we normally expect? Does that actually lower our energy or not? So basically all of these settings are just there so that we can say, okay, we've got enough ingredients, we can get a decent representation of what our orbitals look like, and therefore the energies. Again, for this one, don't worry about changing any of these. It's one of those things where I kind of want you to understand the general concept of what a basis set is, but the specifics about what any of these do is less important. It's just, if you understand it in the concept of, it's all the functions we can mix together to make molecular orbitals, that's what I'm looking for.
Should I throw in one of them? You said it's 6-311.
So this is just the comments, so it's not really gonna make, a difference,
Okay, yeah, you're right.
so, but it would be.
And like if we go back to this part that builds our system for us. It has 6-31 G star versus 6-311 G double star versus 6-311 plus G double star versus these even larger systems. The G in this case actually stands for Gaussian because they're all Gaussian functions in 3 dimensions. So that's basically showing the probability distribution of the electrons. But then they're basically from left to right, they just get better. We don't need to know the specifics of it at this point. Either 6-31 G star or the 311 G double star are both good enough for us. Then last but not, so some of these are the ones you actually might have to change. When you make your initial guesses for your geometries, so stat PT group, the stat PT is basically controls the geometry search. So everything up to this point was actually looking just at the individual energy of a single point. If you actually wanted to do an optimization or a saddle point search, we also need to control how it does that. So, and your optimization is going to be made up of a series, just like you're finding your molecular orbitals was made of a series of calculations where it's looking for potential energy minimum. The geometry works the same way, except it's optimizing where the atoms are, whereas looking for the individual energies, the single point energies, was looking at what orbitals do I mix together to get the lowest electronic energy. But it was keeping all the nuclei still. So basically we have levels of these iterative processes. The whole thing is an iterative process looking at the atomic orbitals mixing together to make molecular orbitals. Then you take that and you do it iteratively moving the nuclei. And every time you move the nuclei, you have to solve for your wave function again. So it basically it's got calculations within calculations. It's feedback loops, right? So the stat PT is basically how many steps will your geometry take before it ends and gives you an error. Because again, you could wind up hung up in a situation where it's oscillating back and forth and will never reach the bottom of a potential energy surface. And if it does that, you don't want it to run forever. You want it to basically stop and spit out an error message. It'll just say failed to reach convergence. And so 30 is more than enough for these small systems. It should be plenty of that's plenty of steps. If it takes more than 30 steps to get to the bottom, your initial guess probably wasn't very good. So sometimes what you do is you just take your output after 30 steps. If it looks like if it wasn't just hung up in an oscillation, but it was actually making steady progress when we look at that graph, if you can see that graph is basically just bumping up and down and never actually not really making any progress anymore, then you probably want to start from a different point. But if it looks like, okay, it took 30 steps, but it's still progressively getting better and better, lower and lower energy, you can basically take your output from that one and feed it back in and do the whole thing again from a different starting point. But for the most part, if you don't get a convergence in 30 steps, try just rearranging your starting point. And so the Hessian, it's just showing me the geometry. It's not showing the orbital energies. It's giving me, or each of these steps is the, well, actually we can run one that's that's not as good to show you what it looks like on a longer one. But basically it's showing you that, if I'm remembering right, the purple is actually the derivative the slope and the blue is the actual energy. And so so basically, if you're not at the bottom of potential energy minimum, then your slope is still significant. And when you reach the bottom of potential energy surface, both the slope should go to 0 and your energy should stop changing. If we wanted to start from a worse starting point for the sake of doing this, so if I just pull one of these up, oh, that's the output file. So basically this bottom part is all that's really going to change for all your geometry optimizations is just the geometry of what you're starting from. If I did something, if I just shifted one of these positions, the Cartesian spot point of one of these, let's just make this 2.08. If I just shift it by half an angstrom in one direction, it might, I'm doing that totally blind without any idea of what that's going to do. I might make the whole molecule fly apart by doing that, by putting two nuclei too close to each other, but let's see what happens. And so the way we do this is I have my input file made with all the system, all the stuff defined. When I put it in here into input file, and I can just hit submit job. Job is being submitted to Jetstream 2. That's the name of the computer that's actually going to run the calculation. And basically, it's basically when you hit submit, it sends that text to the computer as an input file and hits run. Oh, so look, so it was the alcohol hydrogen was the one that I tweaked. And so we can watch this in real time. It's a small enough molecule, it's going through these calculations pretty quickly. If you want to re-show the whole thing, we can hit animate minimization. And see, it's not really giving the right. So, and here's the output file that is writing in real time. So gears obviously are showing that it's still calculating. This is what step it's doing. There's iteration, response error. Did it improve or not? This is all running. This is doing the. Hey, it worked. It finished up. So now if we go to the output file, we can hit download output file. And you can just open with, if you can find Macmol PLT, but I don't think it's actually installed in here. I think I have to download it and then open it that way. Now, if I close out of here, so you have, your computer should be able to do this a little bit better. So it took 20 steps to get to the geometry this time because we started from a worse spot. We started here. And as we go, it got closer. Everything else sort of tweaked, and then it sort of settled into position. Right. And if we look at what the energies looked like for that. So the blue is the actual energy. So the blue was constantly moving back at the same time, but we hit a little weirdness where we actually where the slope got really wonky there. And that's probably right around when it did that, when it did see how the first step after it got that weird slope. It actually moved the two carbons further apart temporarily. And then it said, whoa, wait a second, and brought them back closer together. and then it settled down.
So when we're making these, we're only gonna be doing the water and ethane.
You're gonna water and ethane for your reactants. You're gonna do ethanol for your products. And then your transition state is gonna look something like this. That's the last calculation we need to run successfully. Is get a transition state that's gonna look something like this. And run a saddle point search. So now that you have some more experience building the transition state. So when you open the transition state up, basically you're just going to take a water molecule and your ethene and you're going to put them close to each other. So it looks kind of like that. And what'll happen so this is kind of what I did initially is I just started from ethene. And I took one of and then I added a water molecule and I oriented the water molecule so that the lone pair from the oxygen was kind of pointed in the same general direction as one of the carbons. And then I kind of I basically dragged the hydrogen so that it was kind of halfway in between the other two. And doing this can be a little bit tricky because you want it to be close enough to the oxygen that it still kind of has that attraction. We basically need to look like that oxygen hydrogen bond is breaking at the same time as the carbon hydrogen bond is forming. Right. And so once you think you've got a good starting point for that, you copy your coordinates. And this is actually the easy part. Once you have your sample input file built, don't change anything in it. All you're going to do is you can actually just come up here once you get it built in MacMol and go up to edit and you can hit copy coordinates. And then when I come back to my files, it's like, okay, here's my input file for the SAD point. I'm going to take this and delete that. And I'm just going to copy and paste. Oh, it only copied the coordinates for the hydrogen because I only had the hydrogen selected. So select everything, then hit copy coordinates. Then when we come back here, it seems like a little thing. When you do that though, you're always going to get a blank line. Games doesn't like the blank line in the data section. Make sure you delete that. And now if we come in here, copy and paste all of this. And so double check, it is run type SAD point, not a DFT. So this run type is the one that you're looking to change if you need to. Everything else we can keep the same. And now we come back here again and paste, submit job. And this one might take a little bit longer because we actually ask it to do a little bit more with the calculation here. While this is running, I'll talk about that other bit. Is this last piece sorry, I guess the number of steps Hessian equals calc. And then down here, this is the section that controls the Hessian. The Hessian is basically, it's kind of like taking the first derivative of all of the atoms of the potential energy surface for all of the nuclei. So if you're doing geometry optimization, if you don't have a good calculation for that, then you actually don't know which way the slope is going. So it's an n-dimensional version of what's the upside down delta that you use in calculus? Gradient. It's basically like potential energy surface of gradients. So
if you can calculate it, that's actually really helpful for figuring out where you are on a potential energy service. How close are you to the bottom? Where should you move? Which direction should you move in order to get closer to the bottom? If you don't have a Hessian, it basically is just gonna move all of the atoms slightly in one direction in relative to each other, and then calculate the energy again and say, oh, that was way up in energy. So if you want it to take good steps, you need to give it a good idea of what the local topography looks like. I mean, for the most part, it doesn't give an analytical answer, it gives you a numerical answer, so basically just kind of gives you a, like a dot. If you can picture like a topographical map, where everything was just like dots. You can't see the lines between the dots, but you can get an idea of where the local minimum is. But basically it's a gradient field.
And it looks like it did finish running here. All right, so this is, when we download this one. This one's going to be interesting to look at because we actually need to know if we found the right transition state. So this one's, we didn't quite get there. So you'll notice it ended on frame, maybe you can't see that, hang on. Frame 31 of 31. Remember, we set it to stop the search after 30 steps. It went 30 steps, and you'll see this RMS. That's root mean squared. So that's basically what is the slope still at that point. If it's not 0, you didn't really find the bottom of the potential. You didn't find the saddle point yet. You took 30 steps. And if we look at the energy plot again, is kind of getting closer. We started really high in energy, so it's a little bit hard to tell. But there's still some fluctuations going on there. And if we actually look at what that steps look like, so here's where we started, frame 0. It's kind of like, it's wiggling around. Look at that, the oxygen's actually turning itself to line one of its lone pairs in sp3 geometry. So it's not, that other hydrogen is not pointed directly away from the ethene, which kind of makes sense when we think about where these lone pairs are going to be positioned, right? But we didn't quite get there yet. But we want to know if we're getting closer to the right one. And so one of the ways we do that is by, we want to actually look at it. So, and this is a good example. So now we have like, okay, we think we're getting closer still. We don't think we're stuck in an oscillation. So we copy the coordinates again, and we go back to our saddle point search, and we take our output from one run and we feed it into the next one.
Oh, so it just gets closer and closer.
It should just get closer. We can also do that by changing end step in that stat PT group, but we don't know if we're getting close. We kind of want to check every 30 steps. We don't really want to just say take 200 steps and let it go for an hour if it's going to be going in the wrong direction.
It's like trying to get CCAM.
Yeah. It's similar in a lot of ways. Let's see, make sure that I copied the right one. Copy coordinates. Sad point. Copy it all again. We go back. We run it again. Probably just a couple more steps because I do think we're pretty close there. Make sure while this is running, I'm getting text. Let me make sure that it's not my. Yeah, no, it's not. All right. Oh, looks like it went. Execution of games terminated normally. That's always a good sign. If it doesn't work, it'll say terminated abnormally.
Success.
Yes, because that just means that the program finished running, not that your calculation finished. So it depends a little bit, and you get really good at chasing down error messages on obscure forums from 15 years ago. When you are doing some of these trickier jobs. So let's pull up. That only took one more step and got there. To frame 202, we were right there, and you can't even see what the change was. Just a real, yeah, exactly. But so sometimes that end step is 30. It's a good, like, don't let it go too far, because the other thing that happens is after 30 steps, things have probably moved enough that the initial Hessian is not a good guess anymore. And so what you do is, so when you start again, if we'd left that just set end step to be 50, it might have taken another 6 steps to get there. Oh, where for 37 steps overall versus taking 1 extra step if we stop to ask for directions basically along the way. And the other thing that's cool here is the way we can show that this is the right transition state for what we're looking at is by looking at the frequencies. We can actually calculate and predict the vibrational frequencies for these geometries and then show what they actually look like. So under sub window, one of the options is frequencies. So and what that does, we can say animate. Basically, I'm asking a lot of this computer right now. But basically for this particular frequency, that is the motion that's happening, is that hydrogen moving that direction. If we did a successful saddle point search, having a negative curvature in that one spot, being concave up in that one dimension, means you should have one negative frequency, which can't happen in terms of actually measuring these frequencies. But from the computational point of view, what the negative frequency means is that that one dimension is concave up. Or sorry, it's concave down. And everything else is concave up. If it's concave up, you get real frequencies. It's concave down, you get imaginary frequencies, which show up as negative. So if we found the right transition state, then it should look like the bonds breaking and forming. Which it kind of does there. It looks like you can even see that the 2 carbons are moving slightly further apart. These hydrogens kind of staying in spots, so as the carbons move that direction, we're actually getting more sp3 character out of the carbons. And we're seeing this bond stretching, and this bond that's not drawn, we can see that that carbon and that hydrogen are getting closer together. Okay, so this tells us we found the right transition state. If you found the wrong transition state, it might just look like ethanol with a methyl rotating, right? Because there is going to be a transition state just with the methyl rotating and bumping into the oxygen orbitals, right? So there's always transition states. So the last step of finding the saddle point is making sure that the imaginary frequency that you have is the right imaginary frequency. All right, and then as far as what your final, some of these other ones, we can actually find, let's see, these are in wave numbers, I believe. So we should have one that looks like, so those are your carbon hydrogen bonds, your sp2 carbon hydrogen bonds. We should also have one that looks like oxygen hydrogen stretch. It's up around 4,000 wave numbers instead of the 3,500 we're used to looking at in an IR spectrum. But basically, that's not a bad approximation, all things considered, for how quick the calculation was. We can actually predict what the IR spectrum looks like and what wavelengths, what wave numbers you're likely to see if we do that Hessian calculation. It is a lot. So what do we actually need to do here for this assignment? We just want to make a really crude potential energy surface. And really, we're not even making a potential energy surface. It's the kind of that look, we might expect it to look something like this. Unless we're calculating the points all along this curve, we actually can't show it as a curve. We actually just show it as energy here, energy here, energy here, just connect it with straight lines. There's our transition state, there's our reactants, there's our products. Unless we go to the trouble of actually calculating all the points along the way, we're not supposed to actually show it as a curve, even though we know it really is. So you're just looking to recreate that really crude 3-point potential energy surface. The last thing I need to tell you about that is the units that it gives you for these energies. It reads out your energies down here. But they're in Hartrees.
Yeah, I think we were expecting something weird.
Hartree is basically the amount of energy that a hydrogen has in its ground state relative to no matter existing at all. So since matter has an E equals MC squared relationship, having any matter is way more stable than having no matter. So basically a Hartree is a huge amount of energy relative to what we're dealing with. So we always need to be looking at differences in energy. That this actual number in Hartrees is, for all intents and purposes, useless. It's only useful in the context of comparing it to something else. And that one, let me double check on the procedure.
So will we be using that lab for this kind of the procedure then? Like it gives us like all the details.
Basically, it has some more information for how to do that. It's just in the context of
The
1,3-butadiene.
compared to.
So you're right. And really, if you have, and actually, I don't even think the lab 4 wasn't even in this originally. I put it there to give you some more background on some of the stuff. But basically, you have a sample input file for an optimization and you have a sample input file for a saddle point. All you really need to change in any of those is your geometries and make sure you're doing the optimization where you're supposed to be and we're doing the saddle point where you're supposed to be. Don't look for a saddle point if you're looking for an optimization. And then once you get the geometries to actually get the potential energy surface, all you're going to do is you're going to change run type to energy and DFT type to MO6-2X. And that should actually be a really fast calculation. You take that and run it. And we should get it on we'll get just a raw energy. It won't optimize the whole thing. It just finds, the reason that we do it with the RHF is because the Hessian, calculating the Hessian with MO6-2X takes a really long time. So we run the Hessian, do the transition state search and everything with RHF, and then take those geometries and plug it in with MO6-2X to get your final answer. And that should give you exited gracefully. I do like that phrasing. And there's your electronic energy at the top. And you want as many sigfigs as you can. So a Hartree is.
I think it says on the lab.
Does it? Okay.
Gives it.
Yeah. Or otherwise just look at the Wikipedia for Hartree. And one Hartree is 2,625.4996 kilojoules per mole. So you're gonna get a really small difference in energy for Hartrees comparing your reactants to the transition state. When you convert the Hartrees into kilojoules per mole, you'll get a number that seems more like what we're used to seeing. Okay,
Would it be the percentage difference between what the archeries and interested in then converted?
correct. Or, I mean, you can convert the answers first, but it won't matter. The main thing is that nobody does anything in Hartrees because it's such an absurdly large number. So you just take it and either put it in kcals or in kilojoules per mole.
And for this lab, so we're looking at the ethene and water.
So yeah, you're gonna have a total of four energies that you need. Ethene and water are your reactants. Ethanol is your product in your transition state. If you don't include both ethene and water, it could be, you should run them as two separate jobs. Don't. But if you leave off the water molecule, ethene to that transition state is going to give you a nonsensical answer. Because you're putting atoms in the transition state that weren't in the reactants.
So transition state, you need.
So transition state, you need both of them, and same for your products because it's an addition reaction. But so it's a total of 4 jobs that you need to run, that you need to get to run successfully to get a potential energy surface. To get it to run successfully. And so anytime it ends on 31, frame 31, it probably didn't finish. You can as long as it didn't hang up, double check that it was still making progress. You can probably do what we did here, copy and paste your coordinates and do it again. And let it get closer. And optimizations usually work a lot faster. Saddle point searches computationally are harder for it to do. And so it's a little bit more finicky to get a transition state. So that's probably where you're going to spend the bulk of your time.
Is the transition
state. All right. Yeah.
Yeah.
So the other thing that, and this is, I told David this as well, this isn't going to be due till next Friday.
Okay.
So
might
if I
be
was,
using this time to
Yeah.
actually study for the exam.
that's what I would be doing.
And
And
then
then
after.
Thursday, when you're done with the test, come back to it, watch the recording, remind yourself how it all works, and you should be good to go.
I've got plenty of lines, it's only turning to you.
Okay, deal. Get them all turned in.
The procedure for the radar and then the. That whole first line that we did.
All right, so apparently the second half of the lecture didn't capture the video. I might try and go find one of my old videos. When I minimized the thing, it turned off the camera. But I think I have close to the same lecture.
Well,
It's gonna be like 3 years old by this point. You'll have the audio at least,
the audio helps a lot.
and some notes, and we can go back over some of this stuff on Tuesday as well, if we're still working on it.